We all know what COVID-19 is and how devastating it has been. What makes the coronavirus so dangerous is how highly contagious it is, as well as the relatively long incubation period of the virus. The CDC states that the virus is thought to be spread mainly from person to person between people who are in close contact with one another. This is the main contributor to this rapid spread of the disease, and so therefore the problem our system seeks to solve. We designed Beat COVID, or the Bluetooth-enabled automatic tracking of COVID-19, to leverage the Bluetooth capabilities of smartphones to detect and remind users that they are too close to another and are therefore at risk of spreading the virus. We wanted to be able to find a way to reliably track the spread of the disease and notify users of any crucial updates in real time. When designing our system, we wanted to make sure we prioritized user privacy. Therefore, we do not use any localization techniques and instead use the RSSI of Bluetooth connections to detect the distances between devices. This gives us the information we need but still conceals the exact location of the user. The way that our system works is that we have each device acting as both a central and a peripheral. Once a connection is established, the central will obtain its RSSI and send it along with its own accelerometer data into an HMM. This HMM gives us an estimated distance between these two devices. If this distance is less than 6 feet, it alerts both users. Additionally, a user can self-report if they have been tested or if they have been experiencing symptoms of COVID-19. If a user self-reports that they have been confirmed, people that have come within 6 feet of them are alerted that someone they have been in contact with has been confirmed. They are not told who has been confirmed in order to maintain user privacy. Users can also see the total number of people they have come in contact with and a breakdown of how many of their connections are confirmed or are experiencing symptoms of COVID-19.
To ensure that the app does not interrupt normal phone usage, it needs to have the ability to run while the app is in the background. However, scanning for and sending out BLE advertisements becomes more difficult once the application is in the background. The frequency at which these operations occur decreases, only specific services can be scanned for, and duplicate advertisements from a particular device are effectively ignored. Initially, we had intended to use the RSSI read from the advertisements that were sent out by peripherals, but given that duplicate advertisements are not processed, this approach could not work. Additionally, these background advertisements could not contain the anonymous ID of the peripheral sending it, and again, we knew we had to come up with another approach. So, to continue receiving RSSI information while the application is in the background, it performs the following steps approximately every second. Firstly, each device begins scanning for a particular service and at the same time begins sending out advertisements for that same service. Then, when a device discovers an advertisement, it immediately tries to connect to the peripheral that sent it and subscribes to its service. The peripheral then proceeds to send its anonymous ID through the service that was subscribed to and then sends an EOM. Upon receiving the ID and EOM, the central reads the RSSI of the connection and then unsubscribes from the service. Then the central disconnects from the peripheral and we repeat from step 1. This workaround helps our app circumvent the restrictions on BLE operations in the background put in place by Apple.
One of the biggest challenges was trying to estimate the distance between two phones using RSSI values. In our first attempt, we tried to extrapolate an equation between distance and RSSI, and then use that to find a threshold for the RSSI value at 6 feet. However, as you can see in the graph, the RSSI values varied too much to be confident in a singular equation. We also found that between the three of us, the RSSI values we measured were very different, which led us to believe that the RSSI is extremely dependent on the environment we are in. This means that using a singular equation would not be applicable to different devices in different environments. To improve this, we tried to smooth out the RSSI values by averaging them across a window. Using this, we were able to find a logarithmic decay relationship between RSSI and distance, as seen in the graph. However, though this averaging method helps slightly, thresholding would not work, as we would miss some notifications at a lower distance. Our third method was to add in accelerometer values and use an HMM to estimate distance. In our HMM, our hidden state was the distance between two devices, and the observations are the RSSI and accelerometer values. We determined that the transition probability would use accelerometer data, since we can integrate the accelerometer values, get an estimated displacement, and then estimate our new state from our old state. For the emission probability, we used the distance and RSSI equation we found previously to find an expected RSSI, and then found a probability distribution of possible RSSI values based on the given state. Then, to use the probabilities to estimate the distance, for each possible new distance, we would find the probability of transitioning to that state, and the probability of seeing the observed RSSI value from the new distance. We would find the new distance that maximizes the product of these probabilities, since that is the distance estimate that is most likely to occur given the observations. Using the HMM, we were able to get better results than the previous methods, as we will see in our evaluation.
These are the quantitative evaluation metrics we measured using different distance estimation methods. With thresholding, we found that we would often tend to classify all distances as within 6 feet, as shown through the high recall value. For thresholding with smoothing, we are no longer detecting everything as inside 6 feet, but we are also now missing the detection of some points that are actually within 6 feet. For the HMM, there is an improvement, showing that we are more accurately detecting the values that are within 6 feet, and are also accurately detecting which values should not be included inside 6 feet. Another aspect of our evaluation was the battery life of our application. We wanted to make sure that the app would be able to run for at least 24 hours in the background. We found that in 4 hours, the battery was drained 8%, so therefore in 24 hours it would drain 48% of the phone's battery by running in the background.